Today we are discussing the fourth colligative property, that is osmotic pressure. So what is osmosis? All of you know about osmosis. What is osmosis? It is the flow of solvent to solution when they are separated by a semi-permeable membrane. That is osmosis. The flow of solvent molecules through a semi-permeable membrane from pure solvent to the solution, or we can say from dilute solution to the concentrated solution. That is osmosis. Here in the picture, you can see in this funnel, a solution is kept and it is immersed in pure solvent. Then what will happen? Solvent will enter into this funnel and the mouth of the funnel is covered with a semi-permeable membrane. So solvent will move into the funnel through the semi-permeable membrane. As a result, what happens? You can see the level of solution inside the funnel is increased to a height of h. It is osmosis. And now what is osmotic pressure? Always there is a tendency to flow pure solvent molecules to solution when they are separated by a semi-permeable membrane. If you want to stop this process, what you have to do? That you can see in the next picture. So here P atmosphere pressure is acting here, it is pure solvent. It is pure solution. So solvent has a tendency to move through semi-permeable membrane to the solution. As a result, what happens here? The level will increase. If you want to prevent the increase of the level, you have to apply an excess pressure to the surface of the solution. An excess pressure is required. And we can consider this excess pressure as the osmotic pressure. So what is osmotic pressure? Osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis, that is, to stop the passage of solvent molecules through a semi-permeable membrane into the solution. If solvent and solutions are separated by a semi-permeable membrane, always the solvent will move into the solution. If you want to stop this process or to prevent this process, an external pressure, you have to apply an external pressure, an excess pressure than the atmospheric pressure to the surface of the solution. And that excess pressure, minimum excess pressure that must be required to prevent the osmosis, that is known as osmotic pressure. It is the minimum excess pressure that must be applied to the surface of the solution to prevent the osmosis. It's called osmotic pressure. And this osmotic pressure, it is a colligative property. So it is proportional to number of particles in the solution. And the experiments shown that it is proportional to molarity, not molality, molarity of the solution. Molarity, number of moles of solute per liter of solution. We know the osmotic pressure is represented by the letter pi. And we have the equation PV is equal to nRT. PV is equal to nRT. That is gas equation. PV is equal to nRT. Very dilute solution. The solute particles in very dilute solutions behave like gaseous molecules. So we can apply the same equation here. Instead of P, what we have to use? Pi. Pi V is equal to nRT, where pi is osmotic pressure, V volume of the solution in liter, and number of moles of solute, R universal gas constant, T temperature. Or we can rewrite that equation as pi is equal to CRT, where C is equal to N2 by V. N2 is to represent number of moles of solute. N2 by V. Pi is equal to N2 by V RT, or pi is equal to CRT. And here, what is the aim of colligative property measurements? It is to determine the molecular mass of unknown solute. So we have to derive an equation which relates osmotic pressure and molecular mass. Pi is equal to CRT. From this equation, it is possible to derive. You know, N2 is equal to W2 by M2. So here, in N2, W2 by M2, when you substitute it, you can see pi V is equal to W2 by M2 RT, or M2 is equal to W2 RT by pi V. It is a useful equation to find out the molecular mass of unknown solute. What are the important use of this osmotic pressure measurement? It is widely used to determine the molecular masses of proteins, polymers, and other macromolecules. Proteins, polymers, and other macromolecules. Why this osmotic pressure measurement is using to determine the molecular masses of proteins, polymers, and other macromolecules? There is a reason. Osmotic pressure measurement is at the ordinary temperature. Again, here we are not calculating a difference, depression of freezing point, difference in the freezing points of solution and the solvent, elevation of boiling point, difference in the boiling points of solution and the solvent, relative lowering of vapor pressure. There also we have to calculate the difference in the vapor pressure of solution and the solvent. But here, there is no need to calculate any difference. Directly, we are measuring the osmotic pressure. Osmotic pressure of the solution itself is a colligative property. So even if the quantity of the solute is very small, we will get a measurable value of osmotic pressure. The value of osmotic pressure is measurable. Some polymers, their solubility that is very low solubility. In such case also, we will get a measurable osmotic pressure. So we can see there are some advantages for this osmotic pressure method, and which are the important advantages of osmotic pressure method over the other methods. The first one, pressure measurement is around the room temperature. Second, molarity of the solution is used instead of molality. Third, as compared to other colligative properties, its magnitude is large even for very dilute solutions. And the fourth one, the technique of osmotic pressure for determination of molar mass of solutes is particularly useful for biomolecules, as they are generally not stable at high temperatures and polymers have pure solubility. Biomolecules on heating, especially proteins, you know, if you heat it, denaturation will take place. They are not stable at a high temperature. So for the calculation of molecular masses of biomolecules, osmotic pressure method only can be applied. Similarly, if the solubility is very low, if you measure other colligative properties, you will not get a measurable quantity. But in the case of osmotic pressure, you get a measurable quantity. So these are the advantages of osmotic pressure measurement. Next topic, isotonic solution. What is meant by isotonic solution? Solutions with the same osmotic pressure at same temperature is known as isotonic solutions. What are isotonic solutions? Solutions with the same osmotic pressure at a given temperature or at the same temperature are called isotonic solutions. For example, the osmotic pressure of 0.9% sodium chloride solution. 0.9% means mass by volume percentage. 0.9% sodium chloride solution is isotonic with the osmotic pressure of the fluid inside the blood cell. So we can use 0.9% sodium chloride solution, is known as normal saline solution, for the injections into the cell. Then there is no problem. No flow of solvent from the sodium chloride to the cell or from the cell to the sodium chloride because they are isotonic. So if there is a higher concentration for the solution outside the cell, then what happens? Surely, if the concentration of solution outside the cell is higher than the concentration of the solution inside the cell, that means fluid inside the cell, surely the solvent molecules will flow out of the cell and shrinking will take place. Such solutions are known as hypertonic. And similarly, if the solution is concentration of the solution is less than that of the fluid inside the cell, then what happens? Solvent will move into the cell. Then what happens? Swelling will take place. Such solutions are known as hypotonic solutions. Here in this picture you can see it. In hypotonic solutions, solvent is moving out of the cell, so shrinking will take place. In isotonic solution, the concentrations are same, so it is not flowing out or not flowing in. Otherwise, we can say the moving out and moving in, that will be in an equilibrium. Here you can see the solvent molecules are moving into the cell in the case of hypotonic solution. So swelling will take place. So in the case of people who are taking more salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis. The resulting puffiness or swelling is called edema. So what is edema? It is the swelling due to retention of water in tissue cells and intercellular spaces. When it arises, if you take a lot of salty food or if you are taking large quantities of salt along with your food, it will happen. Water movement from soil into plant root is partly due to osmosis. Through the process of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels and dies. To preserve meat, we will use salt. How it acts? The bacteria on the salty meat, because of the high concentration of salt on the surface of the meat, the water from the bacteria will flow out. That's it shrivels and dies. That is the principle behind it. Actually, it is osmosis. Another important thing, reverse osmosis and water purification. From the seawater, you can make fresh water by reverse osmosis. Here in the picture, you can see an arrangement. Salt water is taken in this compartment, and here you can see pure water, And these two are separated by a semi-permeable membrane, SPM, semi-permeable membrane. And when you apply a pressure more than the osmotic pressure here, what happens? Solvent molecules in the salt water will move through the semi-permeable membrane and will reach here. If we can remove the fresh water continuously, the process will take place continuously. Thus, you will get fresh water continuously. It is reverse osmosis. What is reverse osmosis? The flow of solvent, pure solvent, from a solution to solvent through a semi-permeable membrane by applying a pressure more than the osmotic pressure. Now, some numerical problems. Calculate the osmotic pressure in pascals exerted by a solution prepared by dissolving 1 gram of polymer of molar mass 1,85,000 in 450 ml of water at 37 degrees Celsius. So, what is the equation? Pi v is equal to nRT or pi is equal to n by v RT. Number of moles n, 1 by 1,85,000. R, 8.314 joule. T, 37 plus 270, 310 Kelvin. Divided by volume, 450 into 10 raised to minus 6 meter cube. We need the answer in Pascal. Pi, osmotic pressure. That we have to find out. And what is the molecular mass of polymer? 1,85,000. So you can see the substitution here. 1 into 8.314 into 310 divided by 1.85 into 10 raised to 5 into 450 into 10 raised to minus 6. And the answer is 30.96. Next question. 200 centimeter cube of an aqueous solution of a protein contains 1.26 gram of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2.57 into 10 raised to minus 3 bar. Calculate the molar mass of the protein. So we have already an equation to find out molar mass of the protein. That means solute M2 is equal to WB RT by pi V. M2 is equal to WB RT by pi V. Everything is given. That is WB 1.26. R, since it is in bar, 0.083. And temperature 300 Kelvin. Pi, 2.57 raised to minus 3. V, 200 centimeter cube or ml. You can see the substitution here, and the answer is 61,039 gram per mole. The third question, a 4% solution of sucrose is isotonic with 3% solution of an unknown organic substance. Calculate the molar mass of the unknown organic substance. So here, the two solutions are isotonic. The first one is 4% solution. What is the meaning? 4 gram solute, that is sucrose, in 100 gram solution, or approximately we can take 100 ml solution. And the second one, 3 gram in 100 ml. Based on this, we can do the calculation. Isotonic solutions have same osmotic pressure. And what is osmotic pressure? Pi is equal to n by V RT or CRT. So pi 1, osmotic pressure of first solution, that is equal to osmotic pressure of second solution, pi 2. Pi 1 is equal to pi 2. That is isotonic solution. What is pi 1? C1 RT. That is equal to C2 RT. RT and RT constants cancel, therefore C1 is equal to C2. Now what is C1? C1 is equal to W2 into 1000 divided by M2 into V. Molarity, equation for molarity, W2 by M2 into 1000 by V. Substitute the value 4 into 1000, divided by M2, 342, sucrose. Molecular mass is 342 into 100, C2. W2 into 1000 by M2 into V, same equation, but the mass is different, 3%. So 3 gram into 1000 divided by M2, that is unknown, we have to find out, into 100. Since C1 is equal to C2, we can write 4 into 1000 by 342 into 100, that is equal to 3 into 1000 by M2 into 100. Therefore, 4 by 342 is equal to 3 by M2, or M2 is equal to 3 into 342 divided by 4 is equal to 256.5 gram per mole. So here we can stop the class. The last part, abnormal molecular mass, I am not discussing here because it is removed by NCERT, and if it is not removed from our syllabus, we can take it after opening the schools. Okay, thank you.